Imagine a world where everything we thought we knew about the cosmos is suddenly questioned. A reality where the laws of physics, which have guided scientists for centuries, no longer seem to add up. What if we were wrong about the very nature of the universe? What if the foundational principles upon which our understanding of space and time is built have been incomplete, or even fundamentally flawed? This is exactly what is happening in the field of cosmology today. For generations, Edwin Hubble's discoveries in the 1920s revolutionized our understanding of the universe. His work led to the concept of an expanding universe, which became the cornerstone of modern cosmology. But what if Hubble was wrong? What if the very universe we thought we understood is far more complex than we ever imagined? Hubble's groundbreaking discovery in 1929 was nothing short of a revelation. Using the powerful Hooker telescope at the Mount Wilson Observatory, Hubble observed distant galaxies and found that they were moving away from the Earth. This observation led him to the conclusion that the universe is expanding. This was a game-changer in the scientific community because, until then, the prevailing belief was that the universe was static. It was Hubble's observations that gave birth to the concept of the Hubble constant, which states that the speed at which galaxies move away from Earth is proportional to their distance from us. This simple yet profound finding laid the groundwork for the Big Bang theory, the idea that the universe began from a single, infinitely dense point and has been expanding ever since. The implications of Hubble's discovery were profound. It opened the door to a new era of cosmology, one in which the universe was not a static entity, but a dynamic and ever-changing one. The Big Bang theory, which Hubble's observations helped cement, became the dominant framework for understanding the origins and evolution of the universe. For decades, the Hubble constant was considered one of the most important numbers in cosmology, offering a crucial way to measure the rate of expansion of the universe. However, as technology improved and more sophisticated tools became available, scientists began to question the accuracy of Hubble's original measurements. Fast forward to the late 1990s, when the Hubble Space Telescope, named in honor of Edwin Hubble, began to yield some unexpected and perplexing results. The Hubble Space Telescope, launched in 1990, provided astronomers with an unprecedented view of the universe. Situated above Earth's atmosphere, it was able to observe deep space without the interference of atmospheric distortion, a common problem faced by ground-based telescopes. The Hubble Space Telescope allowed scientists to peer deeper into the cosmos than ever before, revealing stunning images of distant galaxies, nebulae, and star clusters. It was during this time that astronomers began to notice something troubling. In particular, the measurements of the Hubble constant seemed to contradict the findings of the earlier cosmic microwave background (CMB) data, which was gathered by the COBE, Cosmic Background Explorer, and WMAP, Wilkinson Microwave Anisotropy Probe, satellites. These satellites had measured the faint radiation left over from the Big Bang, known as the CMB, and used this data to estimate the age and expansion rate of the universe. The problem arose when measurements from the Hubble Space Telescope, which relied on Cepheid variable stars and Type Ia supernovae to measure cosmic distances, yielded a much higher value for the Hubble constant than the one derived from the CMB data. Cepheid variables are stars that pulse in a predictable way, and by measuring their pulsation periods, astronomers can calculate their intrinsic luminosities. By comparing this intrinsic brightness to the observed brightness, astronomers can determine the distance to these stars. Type Ia supernovae, which occur when a white dwarf star in a binary system reaches a critical mass and explodes, are also considered reliable standard candles for measuring distances in the universe because their intrinsic brightness is well understood. By observing the brightness of these stars and supernovae, astronomers can determine their distance from Earth and, by extension, measure the expansion rate of the universe. Yet when the Hubble Space Telescope began to measure these distances, the results did not align with the predictions made by the CMB data. The discrepancy was significant. While the CMB data suggested that the universe was expanding at a rate of around 67.4 kilometers per second per megaparsec, the Hubble Space Telescope's measurements suggested a rate closer to 73.0 kilometers per second per megaparsec. This difference, known as the Hubble tension, was not just a small statistical anomaly. It was a major contradiction between two sets of data that were both considered to be reliable and accurate. At first, many scientists assumed that the discrepancy was simply the result of measurement errors or uncertainties in the methods used by the Hubble Space Telescope. After all, these are incredibly difficult measurements to make, and small errors can accumulate over vast distances. However, as more and more data was collected, it became clear that the tension between the two values was not going away. In fact, the discrepancy seemed to be growing, leading many cosmologists to question whether our understanding of the universe's expansion was fundamentally flawed. The Hubble tension is not just a small problem in the world of astronomy, it has profound implications for our understanding of the universe as a whole. If the value of the Hubble constant is indeed different from what we've been led to believe, it suggests that there may be something missing in our current models of cosmology. It could indicate that the expansion rate of the universe is not as constant as we once thought. Or, more intriguingly, it could point to the existence of some new force or phenomenon in the universe that we have yet to discover. This leads us to a very exciting possibility: the Hubble tension could be the first clue in a revolution in physics. For nearly a century, we have built our understanding of the universe on the framework established by Edwin Hubble and the Big Bang Theory. But what if that framework is incomplete? What if there are forces and phenomena in the universe that we simply cannot explain using the current model? The Hubble tension could be the first indication that our entire understanding of the universe is about to change. Many scientists believe that this discrepancy may be a sign that there is a new force at work in the cosmos. So far, our understanding of the universe has been based on four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. These forces govern everything from the motion of planets to the behavior of subatomic particles. But what if there is a fifth fundamental force, one that operates on cosmic scales and affects the expansion of the universe? This fifth force could explain the discrepancies in the Hubble constant and provide new insights into the nature of dark energy, which is currently believed to be responsible for the accelerated expansion of the universe. Dark energy is one of the greatest mysteries of modern cosmology. It is a form of energy that is thought to permeate all of space and is believed to be driving the accelerated expansion of the universe. However, despite extensive observations and research, scientists have been unable to directly detect dark energy or understand its true nature. If the Hubble tension is indeed caused by a new force, it could suggest that dark energy is not as simple and unchanging as we once thought. Perhaps dark energy is dynamic, fluctuating over time, and its behavior differs on large scales compared to smaller scales. This would have profound implications for our understanding of the universe's past, present, and future. Another exciting possibility is that the discrepancies in the Hubble constant could be related to the behavior of dark matter. Dark matter is another mysterious component of the universe that, like dark energy, has never been directly observed but is believed to make up a significant portion of the universe's mass. Dark matter exerts gravitational forces on visible matter, and its presence has been inferred from the motion of galaxies and galaxy clusters. However, like dark energy, dark matter remains elusive, and we still don't fully understand how it behaves. Could dark matter be interacting with dark energy in ways that we don't yet understand? Could this interaction be responsible for the accelerated expansion of the universe and the discrepancies in the Hubble constant? While we have made tremendous progress in understanding the fundamental particles that make up the universe, much remains unknown. The standard model of particle physics has been incredibly successful in explaining the behavior of most subatomic particles, but it is incomplete. There are many unanswered questions, and new discoveries are being made all the time. For example, in recent years, scientists have discovered new particles that don't fit neatly into the standard model. Some of these particles behave in strange and unexpected ways, suggesting that there may be unknown forces or interactions at play. The Hubble tension may be the first indication that we need to expand our current understanding of physics to account for these new discoveries. It could be a sign that the universe operates on principles that we have yet to uncover, and that the forces and particles that govern the cosmos are far more complex than we ever imagined. If this is the case, the Hubble tension could be the key to unlocking a whole new chapter in the story of the universe. The launch of the James Webb Space Telescope, JWST, in 2021 brought even more unexpected results that further challenge our understanding of the universe. The JWST, the most advanced space telescope ever built, is designed to peer deeper into the universe than any telescope before it. It uses infrared technology to observe distant galaxies, stars, and other cosmic phenomena that are invisible to other telescopes. When the first images from the JWST were released, scientists were stunned by what they saw. The telescope's observations revealed galaxies that were far more advanced and luminous than expected for their age, suggesting that the universe's evolution may have been much faster and more complex than previously thought. For example, the JWST observed galaxies that were already fully formed just a few 100 million years after the Big Bang, much earlier than the standard model of cosmology predicted. These findings contradict the lambda-CDM model, which is based on the Big Bang theory and the assumption that the universe evolved gradually over billions of years. The JWST's discoveries raise serious questions about the timeline of the universe's formation and the role that dark energy and dark matter played in shaping its structure. In addition to these revelations, the JWST also observed supermassive black holes that were already present in the early universe, black holes that are so massive that they defy the conventional understanding of how such objects can form. According to current models, black holes of this size should not have been able to form so soon after the Big Bang. These findings suggest that our understanding of black hole formation and the evolution of the universe as a whole may be deeply flawed. As more data comes in from the JWST, it is becoming increasingly clear that the standard model of cosmology, which has been the foundation of our understanding of the universe for decades, may no longer be valid. The Hubble tension, along with the unexpected discoveries from the JWST, could signal the dawn of a new era in cosmology, one where the laws of physics are far more complex and dynamic than we ever imagined. The questions raised by the Hubble tension are not just theoretical, they have real implications for our understanding of the universe and our place within it. If the standard model is incorrect, it means that everything we thought we knew about the universe could be wrong. It could change the way we think about the origin of the cosmos, the nature of dark energy and dark matter, and even the fundamental forces that govern the universe. The discoveries made by the Hubble Space Telescope, the James Webb Space Telescope, and other observatories around the world have opened up new frontiers in our understanding of the cosmos. But these discoveries also point to the fact that we are on the cusp of a new era in physics, one where the mysteries of the universe are more complex than we ever imagined. As we continue to explore the depths of space and push the boundaries of our knowledge, we may find that the universe is far stranger and more wondrous than we could have ever dreamed.